Okay, discussing calorimetry. Calorimetry means energy transfer inside of a calorimeter. Calorimeter will measure the amount of calories in a chemical reaction. We can determine these enthalpy changes of a reaction by figuring out how much energy water absorbs or releases. The energy transferred from the particles to the surrounding water is equal but opposite in sign. In other words, if the reaction is giving off energy, the water is taking that energy. So minus Q, or minus energy of the reaction, is equal to positive Q of the surrounding water. We will assume no heat loss to the calorimeters that we use in our classroom, although in reality there's probably going to be some heat loss because here's how one calorimeter is constructed. We will take two coffee cup calorimeters nested together. We'll have a lid on it and we'll stick a thermometer into it so we can measure the temperature change of the water on the inside. Whatever reaction takes place on the inside, we will measure the surrounding temperature water temperature change, and we'll use our calculations to figure out how much energy is transferred from the particles to the surrounding water, or conversely from the water into the system. All right, another benefit of this is we can use it to identify specific heat capacities, which I told you guys is like a fingerprint for substances. All substances have unique fingerprints or unique specific heat capacities. We know the heat capacity of water is 4.184 joules per gram degree Celsius, but oddly enough, different substances have their own unique one, like different metals, like aluminum's 0.895 joules per gram degree Celsius, and brass is 0.340 joules per gram degree Celsius. So we will do a lab where you try to identify unknown metal substances by comparing the calculated specific heat capacity you got from the calorimetry experiment to this list. For example, let's try this problem together. A 5 kilogram piece of metal is heated to 120 degrees. It's placed into 100 mils of water at 25 Celsius, and the water starts going up in temperature. Okay, that makes sense. A hot object gives energy to the cold water. Water heats up. Now, what's the specific heat capacity and the identity of the metal? Okay, so what we'll do is we will set up a little bit of workspace. So I'm going to zoom in here. And you guys are going to be along with me, probably in a little bit of notes. So this one problem we'll do together. We're going to set up the metal that's unknown, and then the surrounding water, and draw two lines. We'll do Q equals, M equals, C equals, and delta T equals for both the metal and for the water. You note that metal is the thing that the specific heat capacity of the metal is what we're trying to solve for. I'm going to put a little question mark there. Now let's start filling in things we know in this question. We know that the amount of water that was placed into the coffee cup calorimeter on the inside was 100 mils. Well, turns out that's 100.0 grams at a heat capacity of 4.184 joules per gram degree Celsius. Now, how much did the temperature go up for the water? All right, from 89.2, starting at 25, so 89.2 minus 25.0 is a total value of 64.2 degrees Celsius positive. Now let's multiply M times C times delta T. So 100 times 4.184 times 64.2. I'm getting a total number of positive 26,861.28 joules. Remember that joules are small, so we need a lot of them for a temperature swing here of water. All right, now the amount of energy that the water absorbed is equal to the amount of energy the metal gave to it. Remember, it's an energy transfer happening in the calorimeter itself. All of that energy is flowing to the waters, but let's make it a negative sign from the perspective of the metal. Now we know that the metal's mass is 5,000 grams because it said 5 kilograms. And here's the tricky part. What's the temperature change of the metal? So this is the only part that's difficult. Okay, the metal started hot at 120, and then it was placed in the calorimeter. It heated up the water. And as the water heats up, the metal cools down. Turns out they both get to the same final temperature. So think in your head, if it starts at 120, gives off energy and ends at 89.2, well, then it must be experiencing a negative 30.8 degrees Celsius temperature change. So I'm going to write negative 30.8 degrees Celsius temperature change. Why negative? Well, because it's going down in temperature, not up. Finally, we can do Q equals MC delta T again, except this time we'll solve for the C by dividing both sides by M delta T. So M's cancel, delta T's cancel. We'll go ahead and plug in negative 26,861.28 divided by the mass, 5,000, multiplied by negative 30.8. All right, in doing that, note that the negatives will cancel out, and we'll end up with a value of 0.174 joules per gram degrees Celsius. Circle that because that's the specific heat capacity of the metal. Okay, now let's zoom out here. 0.174. Notice what is closest to that value. So it's not aluminum, not brass, copper, cobalt, gold, iron. So it looks like it's going to be lanthanum. So the identity of the metal in the coffee cup calorimeter, that piece of metal that's unknown, is lanthanum. All right. So again, in summary, the energy given to the water is equal but opposite in sign. You need a well-insulated calorimeter so there's no energy leakage to the outside, and we'll use a thermometer to measure the temperature changes. Okay, you might now go ahead and open up this problem set called the Calorimetry worksheet. There's 6 questions. I'd like you to attempt the remaining 5. Let's go ahead and attempt to solve the first one together. Actually, not number 1, but let's do the last one on the front page, which is number 3. A 20-gram sample of metal is at 100 Celsius. The metal is placed into water at a temperature of 23. The water heats up and the metal cools down. They both reach 29.5. What's the specific heat of the metal? Again, what you guys will be interested in doing is doing the metal on the left and the water on the right. Q equals, M equals, C equals, delta T equals for both the water and the metal. We're still going to be solving for the C of the metal. The mass of the water is 100.0 grams, 4.184 joules per gram degree Celsius. The temperature change of the water in this case is 6.5 positive degrees. Now we multiply it out. And I got 2,719.6 joules positive. That would make this one negative 2,719.6 joules. The mass is 20.0 grams. And the delta T is from 100 down to 29.5. So that would be negative, what would that be? Negative 70.5 degrees Celsius. Same thing, you're going to take this divided by 20 times 70.5. So let's do that. I'm getting a value of 1.93 joules per gram Celsius. Negatives will both cancel out, leaving us with a positive specific heat capacity. Now, hey, we could go back and try to identify that metal. 0.195. Okay, also lanthanum. It looks like we got the same exact answer. Okay, I hope that was helpful. Go ahead and get some work done, and best of luck on your calorimetry problems. Bye now.